So we have seen when the index or the element is known. What if the index is a large constant like 1024? Will we be doing this manual multiplication? Or what if the index is a variable? We frequently use this kind of statements in order to access elements in a list or an array periodically, iteratively using loops, right? So we have to calculate the address with the help of instructions. How we can do that? Any idea? So for example, if I have to execute this thing in a loop, you have already studied how loops are implemented. So I corresponds to the element. Let's say initial value of I is 0. So first of all, it should access 0, and then next element should be 4 to access the A1. Similarly, A2 would correspond to 8, and so on. So we cannot specify the hard value, like constant value. What do we do then? You have studied, yes? Huh?
You could store the variable, the large constant, with the temporary register.
Now how do I increment? Because we have to periodically increment the value. Yes, Meg.
Well, because you can't change the offset, you can change the actual address. Like, so instead of using offsets, you actually just add the offset.
Offset. And how we can keep incrementing the offset?
In a loop.
Yes, in a loop. What instruction we can use? Remember that we are multiplying every offset value with 4.
Yeah.
And we have already seen how we can get the any value multiplied by 4 with the help of shift left logical instructions. Okay? So array indexing, we have already talked about this already, multiplying index by element size to get the offset value, and we need to add the offset to the base address. So here, if we have to calculate a address of A1024, so first of all, what we are doing here is, this is the base address. Assume that 1024, we are initializing it into a variable t0, temporary variable 0. Okay. Now we can multiply this constant value by 4 with the help of this instruction. So shifting it twice means we're multiplying the value by 4. It will give us the offset value. Okay. And then what we do is t0, which contains the actual offset, plus s1. S1 corresponds to the base address, safe register containing the base address. Then we will get the effective address, the entire address in t0. Okay. Now we have the complete address S1, which is the base address, plus the offset in t0. We need to use this in the instruction, in load word instruction. We have already calculated the offset plus the base address, which is the effective address. What we are going to specify in the instruction in place of offset? Y1? 0. Okay. Okay, so before we talk about that, I would like to also talk about how we access the ith element. Okay. The logic is same. We just keep multiplying the value of S2 and storing it into T0, assuming that S2 contains the value of I. We just keep multiplying it, and T0, which is now offset, is added to the base address S1, and then store in T0 again. So this is making the effective address. Effective means offset plus the base address. Okay. So can we write it like this? LWS2 T0 S1. I have already discussed this conversation. No, this is incorrect, because now T0 already contains the effective address, which is the base address plus the offset. So this is wrong. The correct way of executing load instruction is now this. Okay. So T0 now contain the base address plus the offset address. So what do we specify in offset? This 12-bit immediate value, we just specify 0. Okay? And then we could access all the elements iteratively in a loop and store the value in S2. Oh, sorry, S2, yes. Okay? Yep.
The bottom right, where you have LW S2 0 T0, that comes after add, right?
Yes, of course.